So we will sort of continue with the overall theme from the morning, right? But again, we would want to go slowly, step by step, and we would want to build things, right? So this session is going to be slightly interactive. Interactive in the sense I am going to sort of use your inputs to slowly grow the concepts or examples, right, from simple to more and more complicated. Okay, so topic of today's session is reinforcement learning. Right. So this is basically an algorithmic paradigm, right? So reinforcement learning these are class of algorithms. Okay, but then these are algorithms for what problems, right? So these are basically solution methods, algorithms, right? So algorithm is a solution, right? So we are actually calling, we are telling the solution name of the solution first, even before telling exactly what the problem is, right? So what we will do is solution methods. So we will also sort of, I would say not or, that is, should say, that is, what we have to first understand is that these are solution methods for what sort of problems. So these are solution methods for sequential decision making problems or sequential decision making under uncertainty. Okay. Okay. This is basically the problem. Okay. So before we move forward, what we want to understand is we want to spend some time on each of these keywords, right? What we mean by sequential, what we mean by decision making, right? And then slowly we should add uncertainty, etc., etc., right? And then this is there is some qualification to the word sequential decision making, right? So in this context, right, just as we say when we say sequential decision making, at least when we are talking about reinforcement learning, it's going to be within a specific, there is a specific meaning to sequential decision making. We will first try to qualify that. Okay, fine. So before we move forward, what we want to understand is, okay, what is the framework that we are in, right? So the framework that we are in is sometimes called the rational agent framework, right? Right, and if you want to know more about this, you should perhaps go and read this book by Russell and Norvig. Okay, it's a good book on AI. Right, this is book is Norvig Russell, and okay. So what is the rational agent framework? The rational agent framework is just the following. There is an agent, okay, or the decision maker, okay, and there is an environment. Okay, so these are two separate entities, right? So what we can imagine is ourselves as also decision makers or the agents, intelligent agents, and then the world with which we are interacting as the environment, right? The environment or This is the world. Okay. Yeah. Things. No, not able to center things. Okay. So what we can do is we can just put these things in separate boxes. Right. So now what happens is that, so the world or the environment contains all information, right? This contains the, oh, okay. This contains full information. Okay, and what the agent receives, right? So agent sort of receives, okay, this doesn't work here. So the agent receives some information from the environment. Okay, I think I am sort of used with the Apple pen that, yeah. Okay. So what the agent observes? It observes some partial information. Right. Okay. And then the agent has to make the decision. Okay. So first within this framework, what we will do is we will play around for some 10 to 15 minutes or maybe 5 to 10 minutes. Okay. Trying to understand, what do you mean by information, right? When we say partial information, what happens, right? Then there is this thing about the decision. What is the nature of decision, right? And once a decision is made, the agent also receives a feedback in the form of a reward. Or there is a loss. Okay. This is the overall setup, right? So what we are going to play around is with the following things: what sort of decision, whether full or partial information, right? And then even the arrow marks. Okay. So these are the things that we can ask questions about in this diagram, right? So as we said, right? So sequential decision making under uncertainty. Okay. So first is sequential decision making, right? So this is what we want to focus on, right? The most trivial case of decision making is, the most trivial instance of this problem is, there is no decision to make, there is no sequence, right? The most easiest of this is, there is no decision to be made, there is no sequence, there is no uncertainty, right? Then that becomes the easiest case, right? Because that's the problem that we are trying to address, and then if there is no decision to make, there is no sequence anyway, right? And then since there is no decision to make, there is no uncertainty, do we still have something to solve, right? At that level, what do we have? What do we have to solve? Okay, fine. So let us just copy this diagram. Okay, then okay. I think it's better I copy the page. Yeah. Okay. Okay. So first set of things that we want to understand is, no decision to make. That means what? So this arrow mark goes away. Okay, you don't have to decide anything. Okay, which means that since there is no decision, there is no notion of whether it was a right or wrong decision. Okay, so the agent is just observing, right? Agent is just observing something from the environment. Okay, so let us call these observations. So once the observation is there, so let us just give some name for the observations, right? So there is some full information with the world, but the agent is just observing some xi I equals 1 to n, right, where these are vectors in some R dimension. So what do we mean by this, right? So what are the examples of such problems? Okay, suppose I give you a bunch of documents. Okay, each document can be represented as a vector. How do you represent each document as a vector? Huh?
By taking word as an element.
Word as an element, but you can tell how frequently each word occurred, right? So you have a vocabulary set, right? So let us say the vocabulary has, say, examples of such problems is, say, document clustering, right? So how is each document? Each document belongs to r to the power number of words in vocabulary, right? You want to store the word count, and that will tell what a document is, right? And then what sort of picture do you want to draw here? So what you want is, so when you want to say document clustering, so what we can think of is the following. Okay, I think I should have. Right, these xis are in RD. I should just say. Okay, so yeah, and maybe move. Oh, sorry. I think I have to get a bit used to it. Yeah. Okay, fine. So here what we can think of is the following, which is, so there is some space, right, and this space you have some points, right, and then these are your xis, right, and then you want to cluster them. Maybe all these are sports documents, maybe all this is related to cinema, and maybe all this is related to politics, right. So basically what you are having, there is no decision to be made, you just have data, and then you are representing data or manipulating data for your own purpose, right, for the agent's own internal purpose, right. So basically here agent manipulates data for its internal representation. Okay, right. There is a reason why I am using the word representation, right, because representation learning, when we say representation learning, when we say deep networks are good at representation learning, this is what we mean, right. There is some observation, and then you are basically manipulating these set of features that you observed, and then creating a new set of features, or manipulating data for your own internal representation. No decision is going to be taken, right. So there is another example again here in the same class. So this is one example. Second example is, say I can look at principal component analysis, right. For example, data is given, say, so there is, say, two-dimensional data. How do we get this? How do I get a straight line? How do I get a straight line? Like this, if I hold it won't be straight. Okay. Now usually if I, in the pad, if you hold it, it will be a straight line. Okay. So principal component analysis is where, so you are given data again, bunch of data. So data is maybe like this, right. Right, which means most part of the data is in this direction and there is less spread in this direction, right. So that means this is the first component and this is the second component, correct. So what you are having is, you are just taking data, seeing where the directions in which the data spread is maximum. So in general what you can do is, you can take a d-dimensional data, look at the top components, right. Maybe there is a million dimensional data, but then you can do a PCA and then you can just retain the top 100 components, right. This is again data manipulation, right. You are not making any decisions. And the third example could be, say, suppose image denoising. Right. So basically you are given data, some image, and then what you want to do is to take the image and then just denoise the image, right. There is no decision as such to make, right. So now all these things, what you are having is what is known as some sort of internal representation learning, right. That is what you learn from data, how to represent, okay. So what we can say is that here the aim, here aim is to take x and then convert it into some phi of x, okay. It is just manipulating data. So this could be in some d dimension, this could be in some d dash dimension, okay. This could be in a different dimension, okay. And this is where neural networks are good at, right. It is just good at manipulating and creating rich data representation, okay. Now that representation can be used for anything, right. It can be, you can use it for classification, regression, or you can even use it for reinforcement learning, right, which is why you have deep reinforcement learning, right. You can have deep networks or convolutional networks to do image classification, that is just a supervised learning problem, but then you are just still using deep learning. So what the deep there does is this internal representation learning, okay. So what we can think of here is that, so the agent is there, so the agent just for its own internal reason takes this and then maps it into some phi x, just internally it is not converted into any decision, okay. So now the next part is where okay. So we have some decision to make, okay, but the decision does not affect the environment, okay. So we still have decision to make. So what I am going to say is that or much before there is a decision, to make, but there is no sequence as such. Okay. So what do we mean by that? Okay. Right. By the way, the paradigm that we are dealing here, where there is no decision to be made, this is nothing but the unsupervised learning paradigm. Okay. Suppose there is a decision to make, there is no such sequence. Okay. So for example, okay. So here again I am going to just modify this image, this diagram. The arrow mark is going to be like this. Then I will explain why that is the case. Okay. So for example, I am going to give you object classification, right, or object recognition or image recognition, right, or image classification, right. I will say image classification. Okay. So let us play this game. So what is this? Okay. And what is this? So what is this? Okay. So in all these things, right? So what is the information that's there with the environment? What is that the agent observes, and what is the decision that the agent, you as the agent, you are making, right? And what is the reward or the loss, right? So can you name that? Then why are we saying there is no sequence here? All these things we have to understand, right? So here what happens? Say for example in image classification, what is the information that the environment has? The environment is, I am the environment, I am showing you this, right? So what do I know? The object, name of the object, right? So what is that you observe? Suppose I show it to a computer, what does the computer observe? Huh? So suppose I show this to a computer, what does a computer observe? It observes pixel information, right? See, it doesn't observe, so what you are observing is not the remote, right? What your vision field observes is the picture of the remote, correct? So this is some image, this belongs to this xi, this belongs to some r to the power pixel cross pixel, right? There are pixels in the x and y direction, that's what you are observing, right? Pixels cross number of pixels. This is an image, right? What you observe is the image, and what we know is the true label, right? The environment has both xi and yi, where yi is the true category of the object, okay, and the decision that you are making is a predictive decision, okay. So this decision is a predictive decision where you want to predict y hat of I, right. So you want to, there is a true category or a true label or with the environment, then what you want to do is to predict what the true category could be, right. So this is the predicted label, correct. So when I say there is no sequence, right, so what is this? So what is the next one? Like anything, right? There is no meaning as such there is no sequential meaning to the entire thing, right? I could have actually shown you this, or I could have shown this, or I could have taken the water bottle and shown anything, right? So imagine, right? So where are we deploying this image recognition or this classification kind of image classification kind of algorithms? So these are deployed in, say you have a Facebook or you have Instagram or Snapchat, right? And then people are uploading images, right? First person could upload their image and with their dog. Second person could upload just a nice sunrise, right? Third person could just upload the image of a house. Somebody could upload an image of a traffic jam. It doesn't matter, correct? So there is no actual sequence, right? And all these decisions, these are just predictive decisions, and this has no consequence on the environment, right? In the morning, when Arun was mentioning, these are things that do not cause any state change, right? Okay. So again, if this is something like a speech recognition, right? So you will have prediction, there will be a sequence, because speech is a sequence, next word actually depends on the current word, etc. But still, as you recognize the speech, it's not really going to influence the speaker, right? The way you are going to, so you are processing what I am saying, what you observe is the audio of what I am saying. The true state of the environment is the word that is there in my mind, right? That's what the set of words that are being spoken. You recognize it and then you want to predict what is that I am speaking, right? But your prediction does not influence me, right? So these are problems again where, so the decision is predictive in nature and the decision does not affect the environment, okay? So here is to predict. Okay. So how does the data here look like? So the data here looks like xi, yi, right? So that's how the data set. So if you go and look at any image classification, say MNIST, CFAR10, any of the classification problems are regression problems, right? What you are having is some observation and then the true value or the true label, and then you want to express, given new observation, you want to predict what is the underlying true category or true label, right? So if you see here, you just have xi's in the first problem where there is no decision to make. Here you have xi as well as yi, okay? And here you can also have a reward, right? The reward is going to be very simplistic, right? This can be just a 0 or 1 reward, right? Which is basically if y hat I equals yi, then reward is 1, else reward is 0, right? So the way you can give rewards also is very straightforward. If you make a mistake, it's immediately known, right? And to some extent, this is the very first thing that even as kids we are taught, right? Somebody shows A for apple, you are shown, it's not only that we are learning alphabets, but we are also learning object categories, right? You are shown a picture of an apple and you are said, oh, this is A for apple, right? And if you observe, that's what we always teach kids, right? Look, that is a dog. Look, there is a bike that is going. Look, this is a car, right? See, that is the moon, right? So this is what we do. We teach kids or children to label things, right? And this is how the data set looks. The data set looks as xi, yi pairs, okay? And the reward is very simplistic in the sense that if you predict a dog to be a dog, you get full marks. If you predict a dog to be a cat, you get 0 marks, right? And that's how you tell the system whether it made a mistake or it did not make a mistake, correct? So again, as you can see, from this picture to the next picture, there is some decision that is being made and there is also some reward that is being given. Right. Here again the internal representation, right, that makes a lot of difference. For instance, you could observe the image, right, and then if you do a linear transformation and then you just build a linear classifier to classify the image, your accuracy is going to be at some level. But then if you use a deep network or a convolutional network to build richer representation, then that transformation of the data is always going to give you better decisions, right. So again here also, even before going through the decision, the agent can do some kind of internal representation and then later convert it into a decision, right. And that is where the representation learning lies, that is where the success of deep learning lies, because anything that is there you can always put this deep module inside, because all that it is doing is take data, take the features, generate richer and richer representations of the data that is given to us. Later on we want to use it for any kind of decision, you are most welcome, right. So this is the second level of set of problems, and this is what is known as the supervised learning set, right. This is basically equivalent to the again characterized. What characterizes supervised learning? Two things: the decision is just predictive in nature, it does not affect the environment, and the reward is very simplistic, it is just 0 or 1 based on whether or not you got the decision right or wrong. Even if it is not, say suppose it is a regression problem, then you are going to have a squared loss. Even there it is a very straightforward function of the distance between the predicted value and the true value, right. The reward is very straightforward, okay. Again here no decision to make, no reward, nothing. Here there is a decision to make, predictive decision, the reward is simplistic. Now we will move on to the most fullest of the setting, right, which is the sequential decision making under uncertainty setting, right. So again we will start with this framework, right. We will have everything here. Okay. Then what we want to look at are what are known as prescriptive or control problems, okay. So where what we are going to do is this, we are going to call it as a state, okay, ST, and we can also assume that in fact the agent has full information about the state, okay. Again note, in the previous setting the computer does not know, if you show this image the computer does not know the true category, right, what it observes it's only the pixels. But here we are saying, you know, the computer or the decision maker can observe the full state. Then what is the challenge, right? The challenge is to come up with a decision which is known as action here, right, and this action actually causes a change in the state, right. For example, you are playing chess, right, you get to observe the board fully, correct, and the action that you make changes the configuration of the chessboard, right. And what happens? You have to change, you have to make action such that you are going to cause a change in the environment that eventually is going to lead to your victory, right. So even though you are totally observing the environment, you can have full information about the environment, even then the decision is kind of challenging, right? It is not just some partial information is there, you have to predict, right? That's the prediction problem. In a control problem, even if you observe fully, the challenge is to actually control the system, right? So this is what is known as a prescriptive set of problems, okay? So in order to take an example from the domain of say medicine, right? So prescription versus prediction, right? So I take a chest x-ray and then say that okay, I am going to predict that with 90% of chance this patient has tuberculosis, right? That is prediction, right? Or I am going to say that oh, this is your blood cholesterol and this is your blood pressure and this is your heart rate, and I am going to predict that within 5 to 6 years you are going to have a blockage in this artery, right? That's a prediction, right? Prescription is where I give you a medicine and then I hope that the situation of the patient actually changes, right? That is what is a prescription. So prediction does not affect the environment, prescription actually affects the environment. Even though you can observe, sometimes you will have partial observability of the environment, that's fine, but the real challenge is even when you observe the environment fully, you still have a challenge, okay? And we will come to the, okay, so here what are the issues? So the key points, the action, causes, to change, the state to change from ST to ST plus 1, right? From ST to, so we will also give some examples and then slowly build, okay? And what happens, it is also true that the reward is RT. So we will talk more about the rewards. Can be arbitrary, is actually arbitrary. That is, in that it does not have any simple structure. Or in other words, environment has full control over rewards. The reward structure actually. What do I mean by that? See here, once you make a decision, the reward is very clear, right? Whether or not it is right or wrong. Here the reward is not very clear, right? So suppose I am playing chess, right? So example here is playing chess, right? Or driving car, right? So when I am playing chess, I make a move, right? Maybe it cost a queen sacrifice, right? My queen got sacrificed, but then eventually I might actually win the game, right? So there is no right or wrong, or like nobody can tell, right? The only way to do is you actually have to play the game, and then maybe the reward is only available in the end. The true reward signal is only available in the end. More or less what happens with life also, right? We make all decisions, right? But eventually, we have to be in a better place, right? So you are making a sequence of decisions so that you are putting yourselves in better and better positions, right? Sometimes you want to trade, for example, immediate reward to future reward, right? Just as you are students, and I have also been a student, and I think I am continuing to be one, right? So typically, not for your age group, but for instance, if you are in standard 6 or 7, the immediate reward to go out and play is extremely higher, right? But then if you study the immediate reward, right, the gratification that you get out of studying is just not as great as going out and playing, right? So if you are having two decisions, either to play or to study, you would always choose playing because playing is immediately giving you some reward, right? But eventually at the end of the year, when we are writing the examination, the study action, if you would have chosen that, that result shows up only in the end, right? So there is this concept of delayed reward, right? So these are some of the what do you call, characteristics of this prescriptive or control problems. Here again, if you look at the data again becomes more and more complicated. So you have to tell what was the state of the system, what was the configuration that you found the system in, for which what action you did, right, what reward you got, and what was the change in the system, right. All this you have to give, and then possibly for entire continual time, right. So if you can see the data set here, the data set is just the observations. Here it is just the observation and the true label, that's about it. Here you have to tell everything. This is what I saw, this is what I did, this is what I received as a reward, and this is what happened next, right. So basically what I saw, this is what I saw this, I did this, this is what happened next. Right? This is where the true sequential nature is, right, because the action affects the decision, affects the next state that you are going to be in. So you are truly controlling the sequence of states that you will visit, right. Everybody, every person is the controller of their own destiny, right, because every time we choose the action so that we go towards the trajectory. We could have been that kid which ignored all the study actions and kept on playing, then maybe all of us are not here, right. So all of us put ourselves here because we chose our trajectory, right. Maybe the immediate rewards are not so great, but then we still chose the actions mainly to move ourselves, put ourselves in a better position, right. That's what you do in chess also. Every time you are making moves so that you are in a better position, you are massaging or manipulating the configuration of the board, right. So that's the aim here, right. The aim here is to take control of the state. So you want to make action so that you want to control the environment. Eventually you want to be in a position where you receive good rewards. Okay. So now what we will do is quickly look at so once I have given this, so what I am going to do is again maybe write down the formal framework of this, right. I mean introduce some terms also here, and then write down some examples, cast some examples in the formal framework, right. So what all do we have here? So what we have is what is known as a, okay, maybe I will go to a new page, okay. You will have a state space, yes, this is the set of all possible configurations that are there. This is set of all then there is A, which is the action space, okay, which is the actions, right, the actions that we can make, right, and R, this is the reward structure. This in general is a mapping, right. R is a mapping from state comma action to reals, right. in this state, if I make some action, I receive some reward, right. Sometimes it is just a map from state to reals, or sometimes it's a mapping from state action next state to reals. I mean, we don't have to bother about it right now. As we look at more examples, we will understand what's happening. Okay. Then we also have what is known as T, which is the transition, okay, which is basically tells us tells how st plus 1 or how st becomes st plus 1 becomes st plus 1 based on AT. Okay. So, quickly what we can do is we can come up with our own problem, right, which is the very first environment that we will or a very useful environment that we will look at is grid world. Okay. So, what we have is this kind of a grid. Okay. Okay, some grid is there. So, can you tell what the states are, what the actions could be? Say suppose there is a grid and then maybe there is a mice sitting somewhere here. Okay. Now, what is the state? What are the actions? How would you describe the transition? How do you want to describe the reward? Now, you can design this. So, what are the states? States are kind of straightforward here, right? What are the states? Position, right? The x comma y coordinate is the state. That's clear for everyone. So, how many states are there here? So, it is basically 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 40 states are there, right. So, we can sort of label the states. This is S1, S2, S5, S6 to S10, then this is S40, S36 to S40, right. So, this is your state space. So, what is your state space? State space is just this collection of 40 states. So, what is the action that you want to give? Up, down, or and you can also say maybe stay, right, up, down, left, right, and I am going to put a dot, dot stays, stay in the same place. It's quite natural, okay. So, now you can choose one of the rewards, right. So, basically what we can do is think that maybe this is the room, right, and then each tile is in a different temperature or something like that, right, and then or there is some kind of temperature or wind or whatnot, and then the reward in that grid tells how comfortable the mouse is going to be if it is in that position, right. So, we can sort of choose the reward to be a function of the state itself, right, or you can model the reward to be some food source and then that is the food that it will get if it visits that state, right. So, what would be a reward? So, this is the states, right. So, what would be a reward structure? These are the states. So, we can cook up our own rewards, right. So, there is also a reason why we are doing this grid world, because it is a very useful example that can be generalized to any other setting. So, can you tell some reward? So, how much do you want How much do you want the mice to get here? You can just tell some numbers. How much reward do you want to get it in this cell? Bottommost? 3. Next one? 7, okay. Next. Choose a number between 0 and 10 or minus 10 and 10. You can also choose negative numbers. 5, okay. Minus 8, okay. So maybe here I will put some 10, 5 minus 3. This is what I mean by the reward can be arbitrary, right? Because that's how the room is, that's how the room is, right? It is not as simple as right or wrong, correct? So you have some rewards, maybe some of them are 0, then maybe there is a 10 here, then maybe there is a minus 10 here, there is also a minus 5 here maybe, so 4, right? You can fill in the rewards, okay. Now what is the transition? So this is also done. This is how the reward structure is. The reward is a mapping from R to state to minus 10 to this set, right. We have chosen integer rewards, we can also put real numbers as rewards. So we also put the rewards. Now how is the transition? Okay, so you have to tell, the transition tells how the state becomes st plus 1 based on action at. Okay, so what do we know? So at, say suppose I am at state, so t of s6 comma up is what? From state s6, if I try to move up, what do I get? Huh? No, so the way I have named this is S7, S11, right, and this is, so if I try to do S8 and if I go left, I get S7, right. So these are what are known as deterministic transitions. Right. So we can also put probabilistic transitions, right. So how will you design a probabilistic transition? So from here onwards, you are just going to grow this example, right. All that we will discuss is just going to be in and around this example. Then I will tell you why this example is kind of general. It's the most general picture that we can have. Okay. So how will you do probabilistic transition?
Toss a coin, either we get a head, then we go right. If we get tails, then we go left. We do something.
No, transition. So that's how we make a decision. You are telling a way to decide, right? I am telling a probabilistic transition. Okay. Why is this realistic? The probabilistic transitions are happening in reality. See, suppose you have a robo, right, and then it's trying to move in this room. Okay. So even though it wants to move, forward, right, there might be some dirt or there might be some stone, and then there might be a small twist in the angle of the wheel, in which the angle in which the wheels are aligned, that it might end up moving actually right. Okay. So in general, whatever actions that you take need not cause the effect that you really want, right. So if the transitions are probabilistic, you can just say the transition itself is probability of going from state 7 or state 7 to state 8, right. I can say probability, if I start from state 8 and I move left, the probability that I will reach state 7 is 0.9. Okay. And at the same time, the action could actually fail with probability 0.1. I try to move left, but then the action failed, so I am staying in the same state. Okay. So this is how you get a stochastic transition. Right, and this is what models the uncertainty. Okay. So now why is this grid world problem very important for us, right? So any domain that you take, right, it can be, you can sort of mentally map any domain to this kind of a grid world, right. So suppose you are playing say chess, right. So each of the state is what? Each of the grid in the state is like what in the chess? A particular board configuration, right, and here you will have left, right, up, down, stay action. There you will have move the pawn, move the bishop, move the horse, some other set of actions, right. Just like from S8 if you move left you will go to S7. Similarly there if you take some board position you would have, you will make an action and then you will just go to some other state, right. So in general if you understand this grid world really well, you would have really understood how to think about reinforcement learning or how to think about the sequential decision making problems for any kind of scenario, right. So you can also map it to a something like a what do you call driving, right. So what is the state? The state is the set of vehicles that you are seeing in front of you, and right, and then in the mirror you will observe some vehicles, right, that is what you observe. So the position of various vehicles. What is your action? The action is the amount of steering control that you have, the brake and the clutch and the accelerator, right, and then once you make the action your vehicle is going to move next, and then there is going to be some movement by the other vehicles also. So there is going to be some randomness, so you go to some other state, right, and then all of that state you can just think that it is similar to the grid position and the action in any environment is similar to the up, down, left, right and stay, and then the reward, right. So here the rewards we have just put this kind of arbitrary rewards. In say something like chess you clearly know the reward is, the actual reward is 0 or 1, 0 if you lose and 1 if you win, or plus or minus 1, minus 1 if you lose and plus 1 if you win, and intermediate you actually get no reward, right, because in between you can lose the pieces, somebody can capture your queen, somebody can capture the bishop, rook, doesn't matter. Finally the opponent might have all the main pieces, you might have a pawn and the king, and or maybe 2 pawns and the king, and then maybe you are able to checkmate, right. So that's possible. So ultimately what matters is whether you won or lost, right. So any sequential this kind of what do you call prescriptive problem or a control problem, you can always think about it in terms of this grid world problem, right, and then randomness is just you are making some action and then you can sort of spread to various different states with different probabilities, okay, fine. So now what we will do is we have to maybe what I will do is I will state the the abstract picture, I will draw the abstract picture of Markov decision processes, right, and then maybe we will break, right. So we have to break now or yeah, maybe I will just state one picture and then we can break and then we can continue, right. So the framework of Markov decision processes, okay. So this is a very the very general picture that you can have. So there are these states, right. So each state is something like this. So there are some n states, right, and then for each action, so you have probability, right, probability of moving from state 1. So there are some actions, action set you can say, there are some k actions. So maybe under action 1 there is a probability with which you will move to state 1, state here, right. For each action there is a different probability, right. So from maybe state 2 under action say J, you want to move to state N, right. So these are the, what do you call, these arrow marks denote the probabilities with which you will transition from state to state under some action, okay. From some state Si, so when you write this term, you say from state Si under action AK, I move to state Sj, right. And in each state you might want to collect a reward, right. The reward will be the state in which, it can depend on the state in which you are in, right. So what we will do is, we will sort of make this picture even more detailed, right, after the break, right. For example, the question that we want to ask is, how is it that we will find out how to move in this, how to make decisions in this environment, right. It is not that clear as to there is no right or wrong answer, right, because if I want to fetch that 10, maybe I might have to go through this -5, right. Maybe if there is a -4 here, maybe I have to go through -4 and then only go to the 10, maybe that is the case, or maybe this 10 is much more easier, right. Maybe there is only one minus here, right, or there is a -2 here, and this 10 is more safe, right. How do we know, right? In general, we really do not know the environment, right, as we are, that is what happens in all of chess, right. None of the chess players know every variation what is the consequence, right. They know already historically whatever game that is being played, what are the states reached, what is the board position reached. If you go and ask any chess player, that is what they will say, right. This position was reached in 1982 so and so tournament, so and so game between this player and this player, right. That is the data that they have. From there, this was the move that led to this thing, but eventually what happens is that they will do a variation, because you really do not want to give the same thing, because then people can just by heart and then play what is already there, right. So in general, you do not know these rewards, but somehow you have to go and make decisions here, right. So the question that we want to answer once we come from the break is, how do we behave, right, how do we behave optimally, so that we make the best of, we collect the best of the rewards. Imagine that I am the mice and this is the food that is there, and then maybe minus is like very old cheese, plus is just new cheese, and then I just want to go around and then keep eating, right, and that is what I want to do. So how do I behave, right, that is the key question about all the prescriptive problems, and that is what reinforcement learning algorithms are going to address, right. So what we will do is, we will slowly develop methods, right. Okay, let us take a break here.